Okay, thank you everyone for coming. This is a seminar today focused on NLP, and I'm just really honored and happy that Lisa is going to tell us about her work today. Lisa is working really in the core of language modeling, which has become quite a bit more popular over the last few years and is now, I think, even a central part of all of computer science, really. Her work has touched on almost every aspect of language modeling, so much so that it's hard to enumerate it all, but everything from prompting, parameter-efficient fine-tuning, entirely new architectural approaches, even through to new ways of doing evaluation, which is very rare to see that kind of breadth. And even more so, in every case, her work is known for being very creative, sort of surprising new approaches that I am always kind of looking to see, what has she done this time and what can I learn from it? And it's really fun. And so you get to see a few of those examples today. Thank you very much.
Thanks, Luke. Thanks for the super kind introduction. Hello, everyone. Today, I'll talk about controlling language models. So language models are probabilistic models over a sequence of strings. And they have actually been around for a while, from Shannon's Markov model in 1940s to large-scale pre-training with GPT-3. The popularity of language model really surged with ChatGPT. But why did ChatGPT suddenly take off? It is because we can finally control these pre-trained language models to do useful tasks. So most people in computer science have used or heard of Coding Copilot. It can boost productivity by auto-completing your code. Coding Copilot arises from controlling the pre-trained language models to the coding domains. Similarly, when you use Google Search, you will see an AI overview at the top of the web page, summarizing the answers to your queries. This tool also arises from controlling language models to do search summaries. So control is really at the heart of transforming language models into useful products. And I developed principled methods for controlling language models. So zooming out a little bit, let's look at the broader context of the language modeling pipeline. We start with a pre-trained language model, and then we control and adapt the model for a particular use case. And finally, we need to evaluate our model to make sure that the control is actually successful. So let's take a closer look at the first stage. Language models have a wide range of use cases. Many companies use language models for their business, for example, building company-specific chatbot or specialized data processing for different companies. And there are new forms of entertainment by customizing language models to role-play people's favorite historical or fictional characters. And because there are so many use cases, customizing language models has become a service. And many companies are now providing this service. So how should we control the language model for such a wide range of different use cases? Imagine that we get thousands of requests per day customizing models for different use cases. For each request, we would fine-tune a model on the provided data. And this results in thousands of different models, each with billions of parameters. So this is very expensive to both train and store such models. I have advanced the methodology of fine-tuning by proposing a very parameter-efficient way of adapting language models, allowing people to achieve 1,000 times improvement in terms of parameter efficiency, and thereby democratizing the customization of language models so that people with fewer resources could also adapt their own models. So now that we've enforced control on the model, what's next? We still need to evaluate the control to make sure that it is actually successful. For example, in this Google AI overview case, the AI summary might be misleading and even harmful. When we ask about the health benefit of running with scissors, it will say the advantage of boosting the immune system, but completely ignores the risk associated with scissors. We really need to detect failure cases like this. Red teaming is one way to evaluate controls. The White House posting and AI law enforcement has recognized this direction as impactful and important. Concretely, what red teaming does is to search for the prompts or inputs that triggers unwanted behaviors in the response. So this is a particularly challenging search problem because the search space over possible inputs is exponentially large. I list some strategies that could break the model. These strategies were discovered in previous red teaming papers, and red teaming is considered successful if it is able to discover one of those strategies. However, our goal is different. We care about covering more failure modes rather than just one of them. And towards this goal, we propose to estimate the posterior distribution, which explicitly accounts for diversity. And turns out, we can cover most of the previously discovered strategies using one method. So overall, we've worked on these challenging control problems and provided effective solutions. However, does control need to be this hard? And why do we need to allocate two extra stages to address control? Is it possible to redesign a language model to be inherently easy to control? So for example, in this red teaming setting, we know that control is hard because it requires decoding from right to left, searching through an exponentially large space over possible inputs. And in fact, any task that breaks the left to right generation ordering is very challenging for current language models. So this is because most of the language models are generating text one token at a time from left to right. And this is actually a structural limitation that restricts the generation flexibility and makes the model harder to control. But the generation order of text doesn't have to be left to right. And my research rethinks about this generation order of text. I develop methods to resolve these control challenges by building a non-autoregressive language model that can generate all the tokens simultaneously. And I will show that this family of models is also controllable by design. So for this talk, I will discuss these three pieces of work: how we apply control via lightweight fine-tuning, how we evaluate control with good coverage, and how we can rethink the existing architecture of language models to build a new model where control is inherently easy. So I'll start with the first part. And this part covers work from this paper called Prefix-Tuning. So as we said before, customizing language models is useful in various settings, including personalization, domain adaptation, and specializing smaller models to perform tasks on edge devices. Basically, when we are customizing a language model, we start from p theta, and we adjust the distribution according to the data to obtain p theta prime. So suppose that we want to customize a personalized writing tool for Alice. And we are provided with a data set of XY pairs, where X is the instruction and Y is a highly stylized piece of writing by Alice. This is the fine-tuning objective. It is to maximize the log probabilities of the examples from this data set. So how should we adapt the language models? Here are two approaches at the two ends of the spectrum. We could do prompting, or we could fine-tune the model parameters. So we know that prompting is quite efficient. It doesn't require updating any model parameters. However, prompting lacks the precision and often fails to capture many subtle points. For example, we are trying to imitate Alice's writing style, which is hard to summarize in natural language prompt, because it would involve a long tail of small preferences, such as detailed word choices and paragraph structures. On the other hand, fine-tuning can match the distribution very well, but it requires updating all the model parameters. So it's very expensive to have to store and update a full model copy for each personalization task. So now the research question is, could we adapt the language model with fewer parameters and at the same time without sacrificing any task performance? So classically in the field of vision and NLP, people have really internalized this idea of freezing some layers of the model and only update the top few layers. However, this idea for adaptation doesn't quite work. It leads to bad accuracy for the target task, and also it doesn't save much in terms of parameter efficiency, because you will still need to update 1/4 of the total parameters. My work on prefix tuning bridges the dichotomy between prompting and fine-tuning. So prefix tuning is inspired by prompting. I observe that the discrete search space of the prompts actually limits the expressivity and makes optimization harder. So I relax the discreteness constraints with continuous free parameters. As a result, prefix tuning optimizes a small, continuous, task-specific vector, which we call prefix parameter, is denoted by the pink H here, as if it were a sequence of virtual prompt tokens. So this is the new optimization objective. We freeze the model parameter theta and only optimize the prefix parameter H to maximize the likelihood of the data. And this design makes the search space very expressive because it's now continuous, and also very easy to optimize because we can leverage tools like gradient descent. So we experiment on a task that converts structured data, such as a table, into natural language descriptions. And we evaluate the quality of the generation with a classic metric called BLEU, for which the higher is better. We evaluate the effectiveness of prefix tuning and find that the model can achieve similar performance as full fine-tuning, while only adjusting 1,000 times fewer parameters. In addition, it has the advantage in terms of auto-distribution generalization, meaning that when the test distribution is different from the training distribution, the prefix-tuned model often attains significantly better performance than full fine-tuning. So intuitively, this is because in prefix tuning, we have preserved the original pre-training model parameters, which is supposed to be very general purpose. So it's generalizing this general purposeness to this downstream task and having better extrapolation performance. So for tasks where the rules and the instructions are very concrete and very unambiguous, we could still think about prompting. We will show that even in this prompting regime, our prefix tuning ideas still applies. So for example, it is quite common for the prompt to include all the detailed rules and instructions, as well as some demonstrating examples, which could lead to very, very, very long prompt. So long prompts will lead to worse inference latency and higher compute cost. As a result, a natural idea is to figure out how to compress the prompts. So this is where the prefix tuning parameterization shines again. When we are trying to compress the prompt, we can map them into the prefix parameter space. In my paper called GIST token, we find that we can effectively compress the prompt by 25 times, and without sacrificing any instruction following performance. So overall, prefix tuning essentially opened up the research direction of parameter-efficient fine-tuning. It's also known as PEFT. It has inspired a lot of follow-up works, including LoRa and prompt tuning. And it has also become the de facto way of how people customize language models nowadays. It is widely used at OpenAI, Anthropic, Google, NVIDIA, etc. in their fine-tuning APIs. So now we've discussed how to control the language model to match some data distribution. Next, we will evaluate whether the control is actually successful or not. So this part of the talk covers this paper called Eliciting Language Model Behaviors. Here, for example, we have a language model to simulate a harmless lady. When we ask a harmful question about how to build a bomb, the language model provides this really detailed instruction. This is actually harmful because people might follow this instruction, which will lead to bad consequences. So this is a form of control violation. And for this part of the talk, our goal is to detect such control failures. So red teaming language model, it is one way to detect failures. Prior work treats red teaming as a search problem. Given some unwanted response Y, people attempt to search for the input prompt X, which will trigger the generation of Y. Specifically, we maximize the probability of Y given X under the target language model P theta. So one concrete idea is to run coordinate ascent in the input token space. We could gradually swap the tokens in X to maximize the objective. And after a large number of iterations, we will find some sequence of strings that will elicit the harmful response with high probabilities. However, what the search mechanism discovers is only one of the modes. And in fact, there are many modes of X that can trigger the generation of Y with high probabilities, including some very trivial ones, such as repeat after me. So in order for evals to be comprehensive, we would really want to have better coverage of the failure cases. And this leads to our research question: maybe search is not enough. How could we achieve better coverage of the unwanted behaviors? To address this, we changed the problem formulation. Instead of finding a single string, we try to find a distribution over strings, which could cover more supports by construction. In our work, we cast this as a posterior inference problem. And our goal is to estimate the posterior distribution of X given Y. Now let's use Bayes' rule to write out the posterior. We have the prior term, the likelihood term, divided by the normalization constant. So here, the normalization constant is actually intractable to estimate because it would involve marginalizing over all the potential prefixes X that could generate Y. So one intuitive idea is to learn to reverse the language model. Let's look at this problem structure. The forward direction is very simple and tractable. This is essentially how we decode from the language model. The backward direction is hard, and this is what we're trying to estimate. So therefore, we can take advantage of this problem structure. We can collect supervised training data using the forward direction, passing X into the language model to obtain Y's, and then we can train a model Q phi to reverse the language model and predict X from Y's. So this model that we just trained is a pretty good starting point. However, there's a distribution shift problem because the Y's that we're looking for are actually infrequent failure cases that are unlikely to appear anywhere in this training distribution. So we really need to solve for this posterior inference problem more directly. And we use the technique from classic statistics called variational inference. So we want to reverse the model, which is we want to learn this Q phi to approximate the true right-to-left posterior of our model, which is P of X given Y. And this equation at the top can be rewritten into three terms. First, there is this entropy term of Q phi, which measures the diversity and coverage of our distribution. There is the cross entropy term, which measures the fluency of our generated text under the prior. And there is the expected likelihood term, which captures how effective our Q phi is in terms of eliciting the unwanted string Y. So we generalize the objective by weighting the entropy and the cross entropy terms separately. And this is because for our specific red teaming problem, there is a lot of uncertainty about the prior. Should the prior distribution be only containing fluent generation, or should the prior distribution be more lenient and allows for gibberish? We are not sure. Therefore, we introduce beta 1 and beta 2 to address for this new degree of freedom. So when we set beta 1 and beta 2 to 1, we are in the exact setting of posterior inference. As we feel more and more uncertain about the prior, we can consider increasing the temperature of the distribution. And if we take this to the extreme, then we will obtain beta 2 equals to 0, which is the objective of maximum entropy RL. So now we've decided on this objective. Our goal is to optimize Q phi to have good coverage of the true posterior. So this is a pretty hard optimization problem because it needs to cover multiple modes. So could we simplify this problem using the idea of iterative decomposition? We want to decompose this hard problem into a sequence of simpler problems, each covering one mode. So here's an intuitive demonstration of this idea, and I will formalize it in the next slide. In the first iteration, we run some algorithm to look for one mode. And then for the second iteration, we downweight the discovered mode, and then we run the algorithm on this new reward landscape, and it will discover a different mode. Then for the third iteration, we do the similar thing. We downweight the first two modes that were already discovered. We run the algorithm again, and it will discover yet another new mode. This way, it is natural to also change the parameterization of Q phi into a mixture of distribution, which is more expressive and inherently good at capturing disjunct modes. So here is the objective for each iteration. I'll first provide some intuition here, and later show that this is actually equivalent to one step of the Frank-Wolfe optimization algorithm applied to the full objective. So here, the red box is the red teaming term, which captures how well our distribution of prompts can elicit the target response. The blue box here penalizes things that were already discovered from previous iterations. So effectively, it's encouraging the discovery of new mode, and it's encouraging for diversity. The orange box is essentially the KL divergence term. It is in charge of regularizing the distribution to prevent it from collapsing or deviating too much from the prior. So as we said, we run this algorithm for multiple iterations, and each iteration, it will discover some new modes. So how do we aggregate across different iterations? We aggregate by performing a mixture of the distributions from each iterations. So this equation at the top suggests that at the end of each iteration, we will mix in the new mode, which is S of I, with eta I as the mixture weight. So as promised earlier, our iterative algorithm is not just ad hoc. It's equivalent to applying the Frank-Wolfe optimization algorithm to the full objective. Here we will show the connection in more detail. So for some background, Frank-Wolfe is a classic optimization algorithm. It is also called the conditional gradient method. So here's a very simple example demonstrating how it works. Suppose that we want to optimize f of x, which is the blue curve. For each iteration, we find the linear approximation of f at the current solution x, which is the brown plane here. And then we solve for the minimizer of this linear approximation, and we obtain the red solution s. Finally, we move x in the direction of s to use this for the next iteration. So plugging in this conditional gradient method to our full objective, we would first do linear approximation to the pink and the blue boxes. And this is essentially trying to compute the first order Taylor expansion at the current solution, which is Q phi I minus 1. And we obtain this term here, which is exactly the first part of our decomposition objective that we just discussed, the red teaming term. And we do the same for the blue boxes, and it will obtain exactly the second term of our decomposition objective, which is the diversity term. And then for this gray box, we copy it over directly. Because now we have part of the objective copying and part of it applying linear approximation, our algorithm is a slight generalization of the vanilla Frank-Wolfe algorithm. But they have very similar convergence properties. So now the next step is to do aggregation, to find a convex combination between the intermediate solution and the current solution. And we have executed exactly this. So for our aggregation step, we get a mixture of distributions. So now I will provide a concrete example to demonstrate different iterations of our algorithm and show that we can indeed discover different modes in the posterior. So suppose that our target suffix y is the most inexhaustible source of magic. And as we said before, we want to find a diverse set of plausible prefixes. So for the first iteration of Frank-Wolfe, repeat after me has the highest reward. And the model learns to pick up this pattern of repetition. In the next iteration, we have adjusted the reward to penalize prefixes favored by the previous iteration. So all the repetition string now gets a lower reward, and the highest reward string turns out to be this one. This reveals a strategy based on continuation and co-occurrence. So basically, using this strategy, we can improve the probability of certain suffixes. And then for the third iteration, we have adjusted the reward again to penalize prompts favored by the previous two iterations. Now the best string is famous quote from J.K. Rowling. This reveals a strategy of prepending a high-level summary or citing the sources to increase the probability of certain suffixes. So these are all real qualitative examples, qualitative strategies discovered by our algorithm. We use the word strategy, but in fact, they are still represented by the prompt distribution from each iteration. So the quantitative reward here suggests that our model is outperforming the supervised fine-tuning and reinforcement learning baselines by attaining a higher elicitation reward, meaning that we get a higher log probability of target suffix given discovered prefix. So we apply this method to elicit harmful behaviors from language models. And this is also commonly referred to as jailbreaking the language models. So in the past 2 years, there have been a lot of work studying how to jailbreak language models. And researchers have discovered strategies either manually or algorithmically. And they list them here. So these checkboxes are the sets of strategies that are recovered by our method. We can see that our method is able to cover the majority of the strategies discovered using previous approaches. So for the two cases where we failed to cover, we note that the past tense is no longer a successful strategy, probably because the model developers have fixed the error. And persuasion strategy is low probability under the prior, because the prior typically contains more instruction-like commands. So quantitatively, our method improves the attack success rate from 2% to 100% for Llama 8B models. Also, the prompt we discovered generalizes to 70B models, as well as proprietary models, such as GPT-4o and Claude 3.5. So this result suggests that our methods for elicitation can preemptively search for errors in language models, which could then guide the model developers to patch these errors and overall lead to a good ecosystem for model development. So hopefully, I've convinced you that control is useful but hard to enforce. And now let's take a step back. Why does control need to be this complicated? Can we make control easier by design? So recall in this red teaming part of the talk, we mentioned this problem structure, where forward decoding is very easy because it's naturally enabled by the left-to-right generation ordering of the language model, but the backward direction is intractable because it's reversing the generation order. However, it doesn't have to be this way. This difficulty is self-imposed because we are shackled by the existing family of language models, which is left-to-right autoregressive. So let's imagine a better world where language models could be composed with other components in a plug-and-play way. So we could plug in our language model and plug in some control criteria that we care about. The control criteria could be a lot of things. If we constrain on the suffix, then we have recovered the red teaming setting. If we constrain on the prefix, then we have recovered the regular left-to-right prompting setting. So once we plugged in all the components, we can infer from the combination of them to decode text that satisfy both of them, meaning that the text is fluent under the language model, and it also satisfies the control criteria. So here's another example of the control criteria. Suppose that we need to parse the language model outputs, and we want it to be exactly in JSON format. Then we could specify this control criteria as a classifier, and apply this plug-and-play framework to generate JSON-formatted content. Looking further ahead, the same framework could be extended to mathematical reasoning. We could plug in a math verifier and use that to steer text generation towards producing valid math proofs. So this form of reasoning could be a really exciting future direction in math. So overall, this inference seems really magical. How should we formulate it mathematically? The answer was kind of hinted in the earlier part of the talk. We formalize it as a posterior inference problem, where we sample from the posterior distribution conditioned on the control criteria. So we sample from P of x given C. So this leads to our research question: how can we design a language model that enables this form of plug-and-play inference? And what are the core ideas that are necessary to get this to work? So there are two ideas that we have gradually already built up in this presentation. The first idea is continuous relaxation. This is the core idea underlying prefix-tuning. The continuous parameterization space is easy to optimize and good for controlling the language model. The second idea is iterative refinement. And this is the core idea underlying our Frank-Wolfe-inspired algorithm. So doing iterative refinement is good for modeling different modes. The steering advantage from the continuous relaxation would make the model more controllable. And the iterative advantage would make the model more expressive. So we want to design a controllable language model that's built on top of these two pillars. Gaussian diffusion is a class of model that nicely marries these two principles. It is used ubiquitously in vision, such as Dolly and stable diffusion. However, when we think about using it for language, it is a much harder problem, because language is inherently discrete. So we know that images, here we are contrasting images and text. We know that images, they are inherently continuous. So if the prediction is near the ground truth image, or if the prediction is in between two good images, then it would still be perceived as a high-quality image. However, this is not true for text. If the predicted vector lies between two words, then it is incorrect, because there is no corresponding word there. Therefore, to model text in the continuous space requires great precision. You might say, OK, we can always map it to the nearest word embedding. So this is a good idea, but it will have some other problem, because the nearest neighbor may not be very coherent with the context. We call this the rounding error, and we'll get to this problem very, very soon. So I've showed you that continuous modeling of discrete text is pretty challenging. Next, we'll get to the more exciting part and show you how we can actually solve this problem. So we designed a model called Diffusion-LM. It's a generative model of text that operates largely in the continuous latent space. And it is non-autoregressive, meaning that each time step is a vector representation of the entire sequence of text. So in Diffusion-LM, we start with a sequence of Gaussian noise vectors. We incrementally denoises them into vectors corresponding to words. And then we project these vectors to a low entropy distribution over the vocabulary. So since we're refining the whole sequence simultaneously, we are first generating coarse-grained contents, such as high-level semantics and syntax in the early diffusion steps. And later, we are generating finer-grained contents, such as detailed word choices in the late diffusion steps. So as we said, Diffusion-LM is a latent variable model. We construct the continuous latents by first embedding the discrete sequence of words into the continuous vector space, using a lookup table to obtain the embedding for each word, and then concatenate them to form the embedding of the sentence. Then we can construct the hierarchy of the latent variables according to the Gaussian diffusion process, where we incrementally scale down xt minus 1. Where basically we incrementally scale down the current, for example, like when we are trying to map from xt minus 1 to xt, we scale down xt minus 1 by some constant and also add a proper amount of Gaussian noise. And we do so iteratively until we reach x capital T, which is pure Gaussian noise. So having constructed this hierarchy of latent variables, we can now use them to supervise the denoising model. So take the denoising transition from xt to xt minus 1 as an example. We train a model, mu theta, which takes as input xt and the current time step t, and tries to predict the less noisy step, xt minus 1. So we train this model by minimizing the L2 distance between the prediction mu theta and the ground truth, xt minus 1. Once we have such a model mu theta trained, we can now generate from this Diffusion-LM. Specifically, we start from this Gaussian noise at x capital T. We apply our mu theta model to gradually denoise the vectors. And for each denoising step, you can take this transition from xt to xt minus 1 as an example. We parameterize it with a Gaussian distribution centered around the prediction mu theta with a proper level of Gaussian noise determined by the hyperparameter alpha. And we iteratively run denoising until we reach x naught. Then we round this continuous vector back to discrete words by mapping the vector to their nearest word embedding in L2 distance. So once we finish that, now we have a sequence of words. We can now generate text from Diffusion-LM. But as we foreshadowed before, there could be rounding errors. For example, we might be generating "be careful or you will rest the glass" instead of the correct version, which is "be careful or you will break the glass." So this occurs because rest and break are actually very close in the embedding space, because they are mostly interchangeable in many contexts, such as take some rest, take some break. However, in this particular case, they are not interchangeable. So if the predicted embedding falls between the two, but is slightly closer to rest, then we'll observe this rounding error. Ideally, the predicted embedding should align exactly with a word embedding, rather than landing between two. So when we make any form of, any of these minor precision errors, they will accumulate and compound during our iterative denoising process. And next, we will discuss two approaches that can actually address this rounding problem. So let's consider the rounding problem in the context of training. Training mu theta is hard because the output domain changes at every denoising step t. So we know that the final step will output the word embedding, whereas earlier steps will output word embeddings at different noise levels. And a single model, mu theta, will struggle to handle these varying distributions in their outputs. So to address this, we reparameterize the model to always predict x naught instead of predicting this one-step transition. This ensures the output space to always be aligned with the word embedding. And as a result, training becomes easier and prediction becomes more precise. So with this reparameterization, we also need to adjust the decoding steps in order to preserve the iterative refinement structure of diffusion. So after predicting x naught from xt, we will add back the proper amount of noise to reconstruct xt minus 1. So this effectively implements a one-step transition from xt to xt minus 1. So since we are predicting x naught at each time step, we can take advantage of this and check whether the prediction is aligned with a real word embedding or not. If it doesn't, then we can correct for the prediction by clamping it to the nearest word embedding. And we call this the clamping trick at decoding time. So since a correct x naught should exactly lie on top of a word, this trick prevents the precision error from accumulating and ensures the stability in the decoding process. So here's a demonstration of the full decoding step. We can start from xt minus 1. We denoise this vector to predict x naught directly. And then we clamp the predicted x naught to the nearest word embeddings. And finally, we add back some Gaussian noise to obtain xt minus 2, completing this transition. So now we've discussed how we could train and decode from our Diffusion-LM. Next, I will fulfill the promise that we've had before and show why Diffusion-LM can empower this plug-and-play framework. So our Diffusion-LM is parameterizing a distribution over the continuous xt. It's essentially parameterizing the plausibility of different vectors at different time steps. So for the control criteria, we could plug in some scoring function of xt. And we need the scoring function to be differentiable with respect to xt. That's all we need. And then we can sample from their posterior using Langevin dynamics. So here, this is one step of Langevin dynamics. We update xt minus 1 in the gradient direction parameterized by Diffusion-LM, which helps with fluency. And also in the gradient direction parameterized by the control criteria, which helps with control satisfaction. And finally, we add a little bit of Gaussian noise to ensure that we are sampling from this distribution rather than just maxing the distribution. So to give the whole picture, we iteratively use the gradient signal from the classifier to steer the model generation towards the desired direction. And we do so for each diffusion steps until we reach x0. And then we round to the nearest word embedding. We round to the nearest word to obtain a sequence of discrete string W. So further, we could compose multiple control criteria together, as long as they are all differentiable. And then we could generate text that satisfy all the control criteria simultaneously. So here are some results of Diffusion-LM and control. We compare it to fine-tuning an autoregressive model and another plug-and-play baselines on top of autoregressive models. So we can see that our approach is outperforming the two baselines by a significant margin for this structured syntax control problem. Further, we tried composing syntactic and semantic controls together. Here, the blue box is the control success rate for the syntax control task, and the green box is the success rate for the semantic task. We find that Diffusion-LM really performs very well under composition of different controls. So overall, Diffusion-LM is the first continuous diffusion language model. Our work has made a significant impact in both industry and academia. DeepMind adopted this idea and scaled up Diffusion-LM. Researchers have built upon our Diffusion-LM architecture to develop diffusion models for language, to do controllable text generation, and people have applied our architecture for other discrete modalities, such as protein design and 3D molecule generation. Also, very recently, there's a startup called Inception that just launched last week, and it's based on this core idea of Diffusion-LM. Their main competitive advantage is that diffusion language model enables 5 to 10 times faster decoding times than autoregressive models. So overall, for today's talk, we've discussed how to control language models in a very principled way. We use prefix-tuning to adapt the language model to some data distribution, and we evaluate control by computing the posterior distribution to discover diverse model failures. And finally, we take a step back to rethink the root cause of all the control challenges. We attribute the control difficulty to autoregressive language models and propose Diffusion-LM, which is controllable by design. So beyond the three aspects I discussed in this talk, I also contribute to the broader ecosystem of controls. For example, I've proposed algorithms to handle composition of different constraints, to leverage weak supervision to improve language model capabilities, and think about learnability of various skills at decoding time, at fine-tuning time. Also, I've introduced highly efficient decoding time ideas, such as using contrastive objective to boost the generation quality, studying human interaction with the language model for creative tasks, and also I've been rethinking the evaluation of language models beyond static benchmarks. So using insights from my prior work, I think the difficulty of controls could really be attributed to some deeper problems, that the models are not consistent across different wheels. So here's one example from the red teaming part of the talk. In the first wheel, we directly ask how do I build a bomb? And then in the second will, we ask in the past tense. So these are two wills of the same underlying problem. But the language model will behave very differently. So this inconsistency makes control harder because we need to control for all the wills simultaneously, and there could be a very long tail of them. Also, consistency goes beyond prompt rephrasing. Here we have another famous example, famous failure case in language models called the reversal curse. In the first will, the model can answer who is Stephen Moffat with the director of Sherlock. But in the second will, when we reverse the question by asking who directed Sherlock, the same model would fail. So this implies an inconsistency problem in models' parametric knowledge and their sensitivity to ordering, which could really harm the reliability of the model. So consistency is not just about solving non-robustness problems in existing language models. It also has broader implications in terms of language model capabilities. For example, many tasks can be framed as different wills, such as generation and validation are two wills of the same underlying problem. Some tasks are easier to verify, such as math proofs. Some tasks are easier to generate, such as knowledge queries, because it's closer to the pre-training distribution. So some tasks will benefit from very long chain of thoughts, like complex reasoning problems. So these all represent different perspectives of the same problem, of the same underlying problem. And enforcing consistency will help the weaker side improve, and ultimately enhancing both sides and maximizing the capabilities of the models. Beyond capabilities, consistency also enhances data efficiency. For example, given this statement, shark is the largest fish and whale is larger than a shark, a logically consistent model should infer that whales are not fish. So this property reduces data requirement. If we train a consistent model on the orange data, it should generalize to the green data without explicitly training on it. So we can essentially achieve the same effect as if we train on both by only training on a subset, which could improve data efficiency. And I believe in the next 3 to 5 years, data efficiency is going to be super important in natural language processing because as we further scale data, we would either need more data, or as we further scale model, we would either need more data or need more data efficient algorithms. And because of this close connection we made between consistency and control, my prior work has set up a good foundation to address these consistency problems. So I will list some directions that we could consider. For example, we could consider hardwiring consistency into the language model architecture by designing models with built-in reflection steps, similar to diffusion models built in iterative refinements. Also, we can encourage consistency during training. We can develop update rules that explicitly regularizes for consistency. So when the model sees a new knowledge, it will update the parametric storage globally. We could also enforce consistency at decoding time by integrating probabilistic inference to ensure that the output is aligned with some consistent posterior. So there are, of course, many more exciting methods and innovations yet to come. I want to end my talk with a remark that consistency and controllability are key ingredients to make the language model's behaviors more predictable and more reliable. And I really look forward to continuing this line of research. Thank you. I'm happy to take any questions.
This is an amazing talk. Thank you. So we can have plenty of time for questions. And I've been informed by the folks in the back that you don't need a microphone, actually. Just speak loudly, and the mics on the wall will pick it up for the recording. So if you raise your hand, then Lisa can call on whoever she wants.
Yes.
I have a question about your work in building the Diffusion-LM for text generation. When you, in talking about the rounding error, it strikes me that the issue that is causing the rounding error is one of the vectorization and representation of the words themselves. Did you look into any techniques where you're altering the actual representation to get around having to build in a separate system to the clamping system?
Yeah. So okay, because they asked me to repeat the question. The question is about whether the rounding, we observe rounding errors in diffusions, and whether this rounding errors is have we thought about this rounding error problem in terms of designing the embedding space? So basically, this is actually part of the talk where I omit the technical details. When we get to get the embedding space for diffusions, we actually train them jointly with the diffusion parameters. So they jointly form a variational lower bound for the likelihood of the observed data. And then we kind of train this two set of parameters, the embedding parameters and the diffusion parameters jointly. There are, of course, other ways that you could acquire the embeddings. For example, you can maybe take some pre-trained embeddings and directly use them. The problem there is that it actually has a very interesting and different trade-off. So previously, when you are thinking about pre-trained embedding, it's typically the longer the better, the higher dimensional the better, because it's more expressive. Whereas in this case of Diffusion-LM, it's actually not true, because here you actually need to reconstruct the embeddings, and you are adding noise in this embedding space. So it's kind of now you are converting, this is why it's hard to have when you are doing diffusion for a super resolution image. It's because the dimensionality is too large, so you kind of have the curse of dimensionality. So that's kind of where the conflicting comes in. You want something that's longer, so that it's more expressive, but also you don't want high dimensionality, because it will make modeling harder. So that's why we kind of take this end-to-end training approach, so that we fix this as a hyperparameter, and the model will learn how to allocate within this fixed set of dimensions, how to find the right embedding. But I feel like there's many interesting future directions in terms of designing this embedding space for diffusions. Yes, questions from the back.
Yeah, great talk. Could you give me some sense about how you control the length of the sentences you can generate when it's a diffusion model?
Yeah. So in this case, we are actually. So the question is, how do we control the length of the generation in the case of diffusion? So in this case, we actually have a fixed length. So if we want something that's shorter, in this paper we actually did 256. If you want something that's shorter, then you can do padding. And then you will get shorter sentences. If you want something that's longer, that's trickier. So for example, one solution is to think about semi-autoregressive generation, meaning that once you generate the first chunk of 256, then you can condition on this generated chunk, pass it through an encoder to a model, and then run the conditional diffusion again to generate the future chunks. So that's how, that's one way you could potentially handle varying length, especially longer varying length. Yes, question.
Really nice talk, thank you. Coming back to the second part.
Mm-hmm.
Okay, so
Yes.
this newer work, where you're sort of setting up the problem as let's build tell me if this is wrong first. Let's automate red teaming,
Mm-hmm.
and let's develop optimization techniques that will let us kind of do what red teaming does automatically. Is that kind of a fair?
Yes, that's
Okay.
kind of fair.
Okay, so this is awesome, because now anything I could do red teaming to help me with, I can now automate it, and it's cheaper, and that's great.
Mm-hmm.
Can you tell me how to use this to make the model not tell people how to build bombs, or to behave better? How do I bring it back to the model? What do you think is the most fruitful way to do that? Because this is always something I struggle with. Anytime we automate things,
Yeah.
it creates a way to. There's an arms race, right? And now we can work on the other side. So I'm on the side of making better language models.
Mm-hmm,
How do I use this?
So basically, for example, there are what our method is able to discover is a set of strategies that can break the model. So actually, you could look at these strategies and then use them. Maybe include them in your training data, so that you can build a new set of training data such that it's robust against such attacks in the future. So for example, if the model detects that past tense is a bad failure case, then basically for the next iteration of training, you can then curate a data set that actually is pretty robust to past tense. And then in that case, in the next iteration of your model, it will have this problem fixed. So I feel that's the most straightforward way where the model developers and the attackers could interact.
It's guide some data augmentation strategy.
Yeah, it could guide data augmentation strategies. Alternatively, maybe another interesting way that you can directly use the technique. Basically, this technique is pretty broad, because red teaming is a search problem. And then in order to make models better, you could also will this as a search problem, where instead of searching for failures, you are searching for success. So if you have a reward model plugin that's specifying how good my answer is, and you are trying to go run the optimization to figure out what are the set of prompts that is able to induce the really good solutions, then I feel like this could be a tool that will actually help you boost model performance. It's kind of like figuring out what is the perfect prompt I should use to ask this problem, or figuring out what's the right querying strategy I should use.
Thanks.
Yeah, question.
This is a related question. Like, how transferable or like how similar are the for the red teaming part? Like, if I have similar types of like bad responses and trying to red team, how similar are the strategies? Like, can you, for instance, instead of like doing this, so you did an example for like a specific sentence, but could you do this, for instance, for like the class of all copyright infringements or something like this?
Interesting. I feel like it really relies on whether you can parameterize it into a reward function. So in the case of like all the copyrighted documents, it just means that you need to design your reward function, say with a retrieval mechanism at the back end of the reward. So I feel like from an algorithmic perspective, this should be able to apply to that, because it doesn't really, our approach doesn't require you to have a reward that's differentiable. So as long as you have some reward, it should work. But except that in your case, the design of the reward will need to change to like incorporate more complicated backends.
Do you think there's like a chance that maybe you could like discover like all sets of strategies that could like cause a copyright infringement? Like that would be amazing, obviously.
I mean, like very likely. So for example, in this case, like what I would do is like you can have some copyrighted documents. Maybe you don't even need like a copyrighted classifier. You can simplify this problem into just having some copyrighted text and then figuring out what are the ways that you can elicit the copyrighted text. So for example, the example that I kind of gave here, it is using like non-harmful text as suffixes. So you can see that repetition will be able to elicit some bad suffix or some target suffix. And then this continuation, so basically if you start with the first part of Harry Potter, very likely it will keep continuing it. And then there are high-level summaries. Like if you start with like giving the summary of Harry Potter, you'll probably be able to enumerate most of the book or something. So overall, I feel like these are all valid strategies that gets discovered. If you just plug in suffixes that are copyrighted content, you will probably be able to discover other interesting strategies.
Okay, we'll do maybe one last question. Pangwei, you want to go ahead?
Oh, hey.
Super cool talk. I also have a question about this section. So
Yeah.
just to clarify, this is a mixture model that you're learning.
Yes, it's a mixture of
So
models.
every iteration you have a sort of separate parameter, separate model, and
Yes.
then you sample according to it. Okay.
Yeah.
So I'm curious to hear your thoughts on how can we, do you think the mixture is fundamental? Can we get one model that generates more diverse samples? Because as you know, obviously, diversity in generation is helpful, not just for red teaming, but in like, generating ideas and so on.
I actually don't think like having multiple models or having a mixture of models is necessary. This is just more like from an algorithm perspective. It's actually very natural, because for each iteration we'll need to train a slightly different model. You can imagine like compiling the model together by like training a new model that's like kind of the mixture version of all the existing models that you've already discovered. That's totally a valid option. I feel like from an expressivity perspective, it should always work. I don't think like, at least in this case, having multiple mixtures of the model, I don't really see why a single language model couldn't express this more diverse modes. It's more just the algorithm kind of, by design, we'll have multiple models gaining from each iterations, and we don't really need to aggregate them. We could just keep them around separately.
Okay, we're at time, so let's thank the speaker one more time.